Okay, we are live now. Hi, welcome everybody. This is our second quantum discussion that we're having here at Chapman University. I'm the co-director of Institute for Quantum Studies at Leifer. I have to say that doing these events online during COVID has reminded me of how much I rely on casual conversations with my colleagues for my sanity, because you know, spending your time thinking about the foundations of quantum mechanics is a pretty esoteric thing to do, and almost everybody around me in my family thinks I'm crazy for doing it. I need to talk to people who are similarly obsessed with the subject in order for it to seem like a normal thing. So I'd like to introduce my guest today, who is Travis Norsen. He's based at Smith College. He is an expert on the foundations of quantum mechanics. He's written a textbook on the subject, an excellent textbook if you are an undergraduate physics major kind of level of understanding. It's a very good explanation of many of the facets of quantum foundations and the interpretation of quantum mechanics. Travis is particularly an expert in ideas about non-locality and de Broglie-Bohm theory. So welcome, Travis.
Thanks. It's great to be here. I look forward to our conversation.
Yeah. So I wanted to start. I'd like to start off by at least acknowledging the situation we're in. You know, it's good that this is something that's allowing us to do this conversation. But how are you coping with the COVID situation?
Yeah, it's definitely strange. I mean, we were chatting beforehand about like teaching and stuff. So my school decided at the last minute, like maybe two and a half weeks before classes started, that they would trash their whole plan of having sort of 50% of students on campus in person and just do everything remote. So there was some kind of last minute figuring out how to transition to that mode. And it's not as bad as I thought it would be. It's actually going fairly well. I'm lucky to have two smallish classes with like 10 or 15 students in each class, and fairly well motivated students that it sort of works well to have it run a little bit more like independent study, and the students doing a lot of stuff in breakout rooms. So you know, the professional life is sort of muddling through, and it's not as bad as it could be. The rest of life, I don't know, is crazy, and I kind of try to play soccer and do remodeling projects on my house to stay sane and things like that. So, but we'll get through it.
So you also do soccer coaching in your spare time. Is the soccer coaching still going on, or are those teams not playing at the moment?
They are playing, yeah. It's sort of restricted, and it has kind of come and gone a little bit, like exactly what's allowed. My younger son's team that I coach, there sort of weren't enough kids on the team whose families were comfortable like playing games against other towns and stuff. So we're just sort of like practicing a couple times a week, you know, playing soccer, wearing masks, which is a bit of a pain. But yeah, it continues and sort of is what it is, and we try to get something out of it and get through to next spring or whenever we're back to normal. So.
Okay, well, I'd like to start the quantum part by asking you a bit about your background. I think that you and I are of pretty much the same generation of physicists. I graduated my PhD in 2003. I think yours was around the same sort of time, was it?
Yeah, I think 02.
02, okay. Yeah, so back then, I mean, probably not everybody watching knows the situation with the field of foundations of quantum mechanics, but you know, historically, at least from the point of view of living in a physics department, it has not exactly been a field that people were encouraged to study. I think it's been, you know, interest has gradually been ramping up, and there are now more PhD and postdoc positions available for it. But back then, certainly it was still a fairly odd thing to do, and you had to be like fairly stubborn or hard-headed to want to go in that direction. And so you originally did your PhD in astrophysics, astroparticle physics. So how did you come around to spending most of your time thinking about quantum mechanics?
Yeah, I mean, I guess so. Yeah, I mean, I completely agree with your sort of description of, this was like a weird thing to be doing back in the 90s or whatever, let alone, the decades before that, when we were too young to be involved. But there were people who had an even rougher time than we did. I mean, my story, I think, is probably a little bit unusual. I went to Harvey Mudd College, which some people might have heard of. I guess it's down in your neck of the woods in Southern California. It describes itself as like the liberal arts college of science and engineering or something, or at least that was their slogan back in the day when I was there. So a very small place, and I had, good close relationships with my physics teachers. I was a physics major and also a philosophy double major. And so the people there were sort of like on the premise of being like friendly to undergraduates and supportive of their interests. And maybe I should mention too, like, how did I even get interested in quantum foundations? I actually just randomly stumbled across David Albert's book, Quantum Mechanics and Experience. At some point, probably like my freshman or sophomore year of college, like I found this book at a used bookstore and read it and was just like, oh, cool. There's all these like interesting controversies about quantum mechanics that I hadn't heard of. And so, I was sort of interested in these things already as an undergraduate, and my undergraduate, physics teachers were, relatively supportive of this, to the point that I think it actually gave me a sort of false impression that this was more of an acceptable and normal thing to be interested in within a physics department. So my sort of like harsh reality came my very first week or perhaps day when I was in graduate school in physics at the University of Washington up in Seattle. And the sort of random guy that I had been assigned as an advisor was like meeting with his new advisees and asked me like, so what are you interested in? I'm like, well, I really like this book by David Albert, and I'm kind of interested in the de Broglie-Bohm interpretation of quantum mechanics and Bell's theorem and these things. And he literally just sort of like laughed in my face and said like, well, that you certainly can't do any of those things here. And so, I sort of read the writing on the wall. I was like, oh, okay, so I'm interested in these things, but this is going to have to be a hobby for me. So I actually kind of, decided at some point, okay, I'll just do a PhD in nuclear theory because I want to get a PhD in physics so I can go kind of teach physics and, pursue my interests in quantum foundations and other things, I guess, more as a hobby. So that's kind of how I ended up being a full-time undergraduate physics teacher who dabbles on the side in quantum foundations.
Yeah, so that book, that David Albert book you're talking about is currently supporting my laptop. Underneath. I would show it to you, but then the whole camera would fall down.
But so is this like a compliment to the book or the opposite of that? It's
well,
a little
it means
weird,
it's one of the few books that I took out of my office when I had to leave campus and brought here. So,
okay.
So compliment. Actually, we used it in teaching. I was teaching a Foundations of Quantum Mechanics course jointly with somebody in the philosophy department here, Kelvin McQueen, last semester, and we were using that book partly for that. Yeah. So yeah, I mean, my story is like fairly similar. I got interested as an undergraduate because of Bell's theorem, which I learned about. Nobody taught me about it in the university, but I learned about it myself. And then when it came time to choose what to do a PhD in, I almost did do a PhD in Foundations of Quantum Mechanics, but I was really, really concerned about the career prospects of that. So I ended up doing quantum information just because it seemed like you could study some of the same types of things from a different angle. But I kind of stayed close to Foundations the whole time. And like when it came time to like finally decide what I was really going to do for the rest of my life, you pursue your passions, right, rather than anything else.
That's right.
That's if you're doing academia and you're not pursuing your passions, that's I think not
You're definitely doing it wrong.
That's a great thing.
Yeah.
So I mean, let's talk a bit about quantum mechanics. So one of the things I liked in your book is if you read a lot of the literature on quantum foundations, I mean, certainly from the philosophy point of view, I'm not saying there aren't more sophisticated views than this, but you get the impression that the main 100% thing you have to do is solve what's called the measurement problem. Okay, so the main idea is to solve the measurement problem, and once you solve the measurement problem, you're done. But you, towards the beginning of the book, introduce what you called the ontology problem as at least equally important. So, I mean, maybe, okay, we need to, since this is supposed to be a general audience level, we need to sort of explain what that is. So perhaps you can give a brief explanation of what that problem is.
Sure. So, I mean, just in case the word is new and it passed anyone by too quickly when you said it, what you were describing as sort of one of, I guess, one of the three problems that I kind of dedicate a chapter each to in the book. One is the infamous measurement problem, which is certainly an important thing that deserves a lot of attention. The second is what I describe as the locality problem. So, of course, that's sort of the whole issue that eventually gives rise to Bell's theorem and these kinds of concerns that I suspect we'll end up talking about tonight a little bit as well. And then the third problem was the ontology problem. Ontology is, I guess, a fancy philosopher's word that just means stuff that exists. And so what is the ontology problem? This is, I mean, I kind of want to like give a little segue into this. So one of my colleagues in the physics department, Smith, happens to be writing a sort of like sophomore level modern physics textbook right now. And so I keep having these discussions with him about sort of like, what is actually like the problem with quantum mechanics? Like, what is the weird thing about quantum mechanics? And of course, you hear all these things like, people say like, well, quantum mechanics involves like consciousness or something, or quantum mechanics is indeterministic. There's like inherently probabilistic, and there's just like all this whole like slate of different things that people claim is sort of like the essential like radical thing about quantum mechanics that, was unexpected or is hard to come to grips with intuitively or whatever. And I basically think that like, 99.9% of the things that normal people have ever heard, even people who are quite interested in quantum mechanics, as a layman, and even people who are like professionals in our subfield, like most of them are just dead wrong about like, what is the actual thing that's kind of crazy and hard to come to grips with about quantum mechanics. Okay. So it's a little bit hard to describe without kind of getting into some kind of technical issues, but the story that one often hears is that, it turns out like, some experiments in the beginning of the 20th century, like started to convince physicists that what they thought were particles were actually waves. And so, okay, sort of developed this like mathematical technology to describe these waves, and these are called the wave function. And of course, it's like a little unclear what the status of this, mathematical object, the wave function is. Seems to sort of play a central role in the mathematics of quantum theory, but it's a little unclear if this mathematical wave function is a description of some kind of like physically real wave that's, propagating around the way that we would think of electromagnetic waves, for example, as propagating around classically, or whether instead, in some sense, I mean, people use words like probability wave, like maybe this thing isn't really a physical thing at all. It's just sort of a description of our knowledge, our incomplete knowledge of, the state of some physical system. So the status of that is unclear. But here's the really weird thing. The really weird thing is that when you deal with a system in quantum mechanics that has more than a single particle in it, so like a 2-particle system or a 3-particle system, or maybe the entire universe, like what most people tend to think quantum mechanics says, or sort of would say, if this is not something they'd thought about, is that like, well, okay, if quantum mechanics says particles are waves, and maybe there's some like confusing thing about the status of these waves, but okay, particles are waves. So if you have 2 particles, then you have like 2 waves propagating around, and maybe they interact in some way, and there's some story about that. But that is just simply not what the theory says. Like the mathematical structure of the theory does not have a wave corresponding in some obscure way to particle 1 propagating around, and then also a wave corresponding in some obscure way to particle 2 propagating around. Instead, it has this really weird sort of mathematically abstract thing. It has a single wave that is somehow for both particles, or for all the particles in the universe, if we're talking about some larger system like the whole universe, which doesn't even live in normal three-dimensional space at all, but instead, so to speak, propagates around in this sort of like high-dimensional abstract mathematical space called configuration space. Okay, so that's just a fact about how sort of standard textbook quantum mechanics for many particle systems works. And it's hard to make sense of that, right? So you can't just say, well, okay, it turns out waves are particles, or maybe they act like waves in certain situations, but then they switch to acting like particles in some other situations. There's like some kind of story you could tell. Like literally, if you just try to take the theory seriously and sort of interpret it in some realistic way and say, look, this object that the theory is kind of all about is evidently some physically real thing, it's kind of impossible, or at least I don't know how to make sense of that. The physically real thing would evidently be something like a wave propagating around in some crazy abstract high-dimensional space, which just doesn't seem to correspond in any obvious way to the three-dimensional physically real space filled with, you know, three-dimensional tables and chairs and cats and people and planets and things, the place that we live. And so to me, that's the ontology problem. How do we even try to interpret quantum mechanics as saying something about what's going on in the world? So that was kind of a long answer, but maybe you can.
That was detailed. That's good. Yeah, so I mean, I think everybody would agree that, I mean, I hope this is non-controversial, that somehow out of quantum mechanics, we have to get the ordinary world that we live in, right? So the three-dimensional world, which has tables and chairs and people talking to each other on Zoom,
Right.
that needs to, that somehow out of the description of quantum mechanics, we need to recover that, because that's just, you know, that's an empirical fact that these things exist.
Right.
I think that you favor sort of local ontology, well, at least what are called, like what John Bell called local beables, or what Einstein called separability. So the idea, I mean, it's certainly true that the easiest way to do that, the easiest way to recover an ordinary three-dimensional world is to have an ordinary three-dimensional world to begin with entities that are localized in space. Obviously, there's a lot of people a lot of approaches in the quantum foundations that disagree with that. So, you know, in the many worlds interpretation, in the last discussion, Sean Carroll was talking about the idea in many worlds that you just take this multi-dimensional object seriously, and you somehow are going to get the three-dimensional world out by sort of a perhaps very long-winded emergence process. But even, you know, within the context of Bohmian theories, there are people like David Albert, who we mentioned before, who still think that all of the fundamental entities live in this very high dimensional space, and that we're sort of just mistaken about the fundamentality of ordinary three-dimensional space. So, I mean, would you defend the position that we need to start in ordinary three-dimensional space?
Yeah, I mean, so there's a lot going on there and many different aspects of that we can touch on. Would I defend the position that we need to start with some stuff in three-dimensional space, some what, as you pointed out, Bell called local beables? I don't know for sure if we need to start with them, but I mean, I think you put it exactly right that, like, if we accept as kind of like one of the things that we know for sure prior to entering sort of relatively high level, sophisticated, you know, advanced experimental science, if one of the things we know for sure is like, look, there's the world sort of three-dimensional, at least in some kind of like macroscopic sense, there's stuff in it and that stuff is real, and this isn't all just some kind of like illusion or something like that. If we accept those things, then, as you said, we need to like be able to reproduce those facts, right? We need our theory, our kind of like fundamental theory of the universe, to be able to account for the real existence of tables and chairs and things like that. And one way to do that, for sure, clearly the easiest way, is to have a theory that has some stuff in three-dimensional space in it. And so of course the the Broglie-Bohm pilot wave theory, which I like, is an example of a theory of that sort. It has particles. So part of the ontology of that theory is there are particles that are just regular literal particles that live in and move around and interact in regular old three-dimensional space. And then there's just nothing remotely puzzling about how to sort of find tables and chairs and the familiar three-dimensional world in what the theory says. Like a table is just, a collection of a bunch of particles arranged in a sort of table-like shape that's relatively stable over time. Okay. So having local beables, something like particles, it doesn't have to be particles, it could be fields or various other things, that is just stuff that exists in ordinary three-dimensional space, having that in the theory from the beginning clearly makes it straightforwardly possible to account for, the things that I think should be taken for granted sort of going in. Now you mentioned like the many worlds interpretation, and you used the word, I can't remember the exact phrase, but use the word emergent, and it's sort of like some long-winded, sort of like blah, 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 lots of hand waving, and maybe the word emergence is mentioned a few times, and then suddenly there's a claim at the end that like, oh, and so tables and chairs exist according to the theory. I've just never been able to understand how to make any sense of that. So maybe you can explain it to me, but I literally don't understand in any of the sort of like possible versions of the phenomenon of emergence that make any sense to me. I've never been able to understand how any of those could apply in a coherent way to saying something like, look, what really fundamentally exists is like a wave in some highly abstract, high-dimensional mathematical space. Or maybe it's even something more abstract like that, it's a ray in Hilbert space. I mean, sort of different equivalent mathematical representations of these things. I don't know what it means for something like a table-shaped arrangement of stuff in three-dimensional space to emerge from something like that. I literally don't know how that would work. So maybe you can help me try to understand.
I don't want to get into too technical of a discussion, but yeah. One thing I can say is that, in the history of physics, we've repeatedly found that things that seem obviously must be true have turned out to be wrong, right? So, even an abstract concept like a field, like a gravitational field or an electromagnetic field didn't, was in some sense the first sort of extremely abstract thing to be introduced into physics, and you could have argued at the time, how can the world be fundamentally made of this kind of stuff? So, I'm not going to defend a particular point of view here, but certainly just sort of, couldn't it be the case that we're sort of very fundamentally mistaken about the stuff that the world is made out of, and that it's only sort of at some very high level of description that things look like they do to us, right? We could just be sort of fundamentally mistaken that the world lives in three-dimensional space.
Yeah,
So we have a question from the audience, which I think I'll interject with, which follows on what you're talking about. What can you say about the extension of the three-dimensional space to 3+1 dimensional space, and can you make the Bohmian theory Lorentz invariant?
My impression is that's probably like a little more technical than we ought to go here, or at least maybe we should cycle back to that after we manage to talk about non-locality and such things. But
yeah, I think we'll talk about specific interpretations a bit later. Maybe.
But you shouldn't, when I say three-dimensional space, you should understand that as perfectly compatible with some sort of relativistic, four-dimensional space-time point of view. I mean 3 dimensions of space, or maybe 3+1 of time, or maybe there's even like some, compactified extra spatial dimensions and these things that like people speculate about for, various kinds of reasons. Like, I'm totally open to all that. I mean, what I'm talking about is as the sort of like abstract thing that I don't know how to relate to that is, the 3n dimensional space, which is where the wave function of the universe lives, where n is some enormous number, 10 to the 100 or something. It's like the number of particles in the universe. It's a completely different kind of thing. So yeah, now where were we?
I was asking, couldn't we be radically mistaken about
Oh, right.
things?
Yeah, I mean, so yeah, so you had talked about sort of the history of physics. I mean, I guess, I don't know, like fields, I mean, you mentioned fields as like, well, we were, you know, those seemed very like abstract and unfamiliar, and people maybe resisted believing in them for a while when they were first introduced. And so maybe this is just like that. I don't really buy that as sort of like a fair analogy. I mean, fields to me, like actually, you know, like, you know, Newton sort of famously said, like, you know, the idea that the sun could exert a force on the earth across, you know, all this empty space is like philosophically absurd. And I think he, you know, explicitly sort of refused as a matter of principle to sort of like speculate about like how it might work that the sun exerts a force on the earth, but he certainly believed that it did. So like, and, you know, I mean, the usual sort of story is like, oh, well, it turns out there's a field, and that's kind of how the sun does it, right? There's this invisible thing that the sun affects nearby, and then sort of that effect kind of like propagates out at some finite speed. And so it's not the, you know, a case of sort of true like action at a distance of the sort that bothered Newton. So my point in raising that is just that, I don't know, like Newton already was kind of like open, I think, to the idea of, if not, I don't know, sort of practically explicitly in favor of some idea like, I don't know, there's some weird like invisible mechanism that I haven't like, we're not sort of in a position yet to like commit to the details of, but there's something going on that I don't know about. And then fields is, I don't know, like sort of the way that that played out. But I mean, it just doesn't strike me as the kind of thing that like was radically shocking to people's worldview, or at very least it probably shouldn't have been if it was. It strikes me as a little bit more like neutrinos or something, right? Oh, it turns out there's some more kinds of particles that we didn't know about, and they kind of like, they're flying around through us all the time, but they don't really interact with us, and so they're kind of invisible to us. But I don't know, like, I don't think that's profoundly troubling to kind of my worldview as like someone who wants to believe that, you know, the stuff I see and kind of like extending out cosmologically from there is like real. So yeah, I mean, I think that kind of analogy massively understates how weird and how unprecedented it is to say something like, well, all of the physically real stuff that, you know, prior to quantum mechanics, we thought was what the world was made of, you know, like atoms and molecules and fields and neutrinos and all these things. Every single one of those things is like some kind of thing that we can give some coherent account of its like moving around and interacting with other stuff in three-dimensional space, or in, you know, 3+1 dimensional space-time. And this is a truly, truly radical departure from that. It's not just saying like, oh, it turns out all that stuff is made out of some other thing that's also in three-dimensional space, and like the detailed wigglings of that other thing, you know, look to us like neutrinos and tables and planets or something. It's rather the true fundamental nature of reality is like sort of so radically different that like, I don't even know really how to characterize it. And then we're told that this other thing emerges from it. Like, I don't know, I guess to kind of go back to the idea of finding historical analogies for what may or may not be acceptable, like it would be helpful to me to understand the proposal if someone could give me a historical precedent for the emergence of some object which exists in a space of some dimension, the emergence of that from something which exists in a space of some other dimension. Because that's like really what I think is needed here. And I mean, correct me if I'm wrong, but I don't think there's any example of that you can give from the history of physics or anything else. It's just completely unprecedented and weird, to the extent that I think most of the people who say this and propose this and sort of think that they understand how it works to the point that they don't need to kind of say anything more. I don't think they've even begun to appreciate how like bizarre and incomprehensible what they're saying actually is. That's the impression I get.
Okay, well, I mean, I guess the reason why I think we should probably move on to another topic, but the reason why I was pressing on this is, my own view about the interpretation of quantum mechanics as things presently stand is that probably none of the solutions that we currently have are right. And it just feels to me like we're missing some assumption, like there's some assumption that we're making that's probably wrong, and that sort of uncovering what that is may help a lot. But people seem to have sort of very different views or ideas, or in order to do that, something has to be given up. And people seem to have very different views on what things it's possible to give up, right? So a many worlds person thinks, okay, localized picture in space-time, we can throw that away because it's not needed. Whereas you have very different ideas about what it's sensible to give up or not. So it's just I'm just sort of probing, trying to probe that in some sense with these questions.
Yeah, I mean, I don't know. I mean, I completely agree with you. I'm also, I mean, I think I'm kind of tend to be known as like a sort of Bible thumping Broglie-Bohm pilot wave type guy. But I'm really not. I really I think compared to many many people who have also written about and spoken about the pilot wave theory, I have a kind of fundamental problem with it, namely the ontology problem. I don't understand how to take the wave function for anything more than a one particle system. I just don't understand how to take that seriously as a physically real thing, because it just doesn't live in the right place, so to speak, to be a physical thing, or even if you ask me, to be sort of physically influencing physically real things. So I'm kind of with you. Like, I feel like, yeah, none of the options on the table seem like they're likely to be the final truth. The pilot wave theory, though, I think is misunderstood by so many people that I don't know, it really isn't it is a kind of counterexample to so many things that so many people, most of whom ought to know better, think is like important about quantum mechanics, or believe to be sort of, the inexplicable core mystery of quantum mechanics. Like it really does just sort of like refute a lot of these points of view that are very popular. And so I can see how maybe I sometimes come off as a big fan of it, even though, yeah, I think it's probably not right. And I don't know how to understand the wave function in it any more than I know how to understand sort of how to make sense of the wave function as a physically real thing in spontaneous collapse theories or in the many worlds interpretation. So, I mean, if you ask me, you didn't exactly, but well, I can pretend that you did. I mean, if you ask me, the sort of like assumption that, I mean, you sort of said in a kind of vague way, you sort of have the sense that it's likely that we're just missing something, and there's like sort of something right in front of us, maybe even, that just turns out to be like completely wrong. I'm fairly confident that the thing that is right in front of us that is sort of wrong somehow is the wave function. And I think what we need to be doing is looking for ways of understanding quantum mechanics that don't involve the wave function, because that's the one part that I at least don't know how to make any sense of in any kind of like coherent physical way.
Okay. Well, maybe we should, as you mentioned earlier, maybe we should move on to talking about Bell and things like that.
Sure, that's another fun topic.
I'm guessing that that John Bell is probably a very big influence on you. Well, I can tell he's a big influence on your work. I think that everybody who is working on quantum foundations probably has, or if they haven't, they need to read his book, Speakable and Unspeakable. Everybody goes through the process of reading that at some point. John Bell also...
but surprisingly few people actually seem to understand the things that he says in the book.
Well, I mean, I think I give him credit as being certainly the clearest thinker about the foundations of quantum mechanics at the time he was working, and you know, especially for a physicist, where these things weren't often discussed. So, you know, it's right that he has a tremendous influence on the field. I mean, I think that there are, you know, he also was discussing a lot the kinds of theories that you talk about, like the Broglie-Bohm theory. But of course, he's famous for Bell's theorem, and we have to discuss it at some point. Bell's theorem and non-locality in quantum mechanics. Obviously, it's a very strange thing, because it's like a sort of deceptively extremely simple mathematical results. The mathematics any undergraduate physicist anyway, even any beginning undergraduate physicist can probably understand the mathematics behind it.
Right.
But still, between sort of 1964, when it was first discovered, and today, there are raging debates about what it all means. And I think that you and I probably have a very similar view about what it all means, but I hope we can sort of get into some of the debates that are going on. But first of all, would you like to say a little bit about what you think, or what Bell's theorem is, and what you think its significance is?
Yeah, sure. I mean, I'm tempted, though, to answer by mostly speaking about things that had happened prior to what Bell showed in 1964, because I think if those other prior things can simply be laid out clearly and understood and agreed upon, then the sort of proper understanding of what Bell did subsequently just kind of clicks painlessly and naturally and straightforwardly into place. And so
you want to talk about Einstein, Podolsky, Rosen first?
That's right. Is that okay?
Sure, go ahead.
So yeah, I mean, so Einstein, Podolsky, and Rosen, and you know what? Let's forget about Podolsky and Rosen, and in fact, let's forget about EPR, because the famous EPR paper is like kind of confusing, kind of controversial. It wasn't actually written by Einstein, and indeed Einstein, it was written by Podolsky, and when Einstein saw the published paper for the first time after it was published, he basically got mad at Podolsky and said something like this is crap, and you buried the main point or something, is what he said. Okay, but you know, so Einstein in several other places in the 1920s and 30s and beyond, you know, constructed this argument, and the argument is so simple that there's just no reason anyone should misunderstand it. So according to quantum mechanics, it's possible to create a pair of particles, and we can, I don't know, use the sort of reformulation of this argument that I guess was due to David Bohm in 1951, but it's the same argument. So it's possible in quantum mechanics to create a pair of particles in what's called an entangled superposition of their spins, in which the particles are in a superposition of like this one being spin up and this one being spin down, say, and then also the opposite way around. So we sort of know for sure that if we measure the spins of both particles, they'll come out opposite. Either this one will be up and this one will be down, or vice versa. This one will be down and this one will be up. And it's like 50-50 chance, according to quantum mechanics, which of those happens. Basically, the wave function describes the state of that two-particle system as some kind of like fuzzy blur between those two possibilities. And the kind of standard textbook rules of quantum mechanics say that that fuzzy blur only sort of collapses down into some one sharp definite reality when you make a measurement on the thing. Okay, I think probably anybody who's watching this video already knows about this. So we'll assume that that's sufficient. Okay, so then what's the argument? The argument is pretty simple. Look, suppose you make the measurement first on the particle on this side. According to quantum mechanics, that collapses the wave function, and the other distant particle goes from being in this weird, fuzzy, nebulous state of not really being either definitely spin up or definitely spin down. It's somehow both or neither, or who knows what English word we should use to describe it. But it's definitely not one or the other exclusively. It goes from being in that funny nebulous state to now either definitely being spin up or definitely being spin down. Okay. And Einstein looked at that and said, look, if that's the story according to quantum mechanics, it can't be right. Like measuring something here causes the system over here to go from one state, namely this sort of like fuzzy nebulous state, to either this or this. It changes the state. And according to quantum mechanics, it does so instantaneously, even though this could be like a million light years away or something. And so Einstein, who you might have heard of as the inventor of relativity theory and the famous associated idea that the speed of light is some kind of like cosmic causal speed limit, Einstein was unwilling to accept this. He described this as a spooky action at a distance, and sort of less poetically, it's a violation of the relativistic idea that causal influences can only propagate at the speed of light or slower. So, and this, by the way, is the locality problem. That's one of the chapters of my book that describes what I think of as sort of the problems with ordinary quantum mechanics that various like realistic interpretations sort of ought to be in the business of trying to address in some way. And so Einstein's suggestion was, look, all we have to do to avoid this troubling sort of relativity violating non-locality that is postulated by ordinary quantum mechanics, all we have to do to avoid that is sort of not take the wave function, the thing that says that the distant particle is in some fuzzy nebulous neither here nor there state, not take it kind of quite so seriously, or at least not take it as providing a complete description of the state of the system. In particular, he said, look, if when we create the two particles, at the source earlier on, before they separate apart, maybe what's happening is every pair of particles is either of this type and then it separates apart and it's like this, or it's of this type and they separate apart and it's like this. And so maybe if we just understand the wave function as describing our ignorance about the detailed state of a thing which has some one definite state, it's just unknown. And then the thing that's collapsing when we make a measurement is not like the physical state of the thing, but just our knowledge. We learn, oh, this was one of the pairs where it was like this. And so the distant particle is like this, but it's always been like that the whole time. We in no way causally influenced it by making a measurement over here. Okay, this was Einstein's argument, point of view. And I think it's just sort of incontrovertible. It's just clear as day, right? In order to avoid the non-local causality that is inherent in the standard quantum description, according to which the wave function provides a complete description of reality. In order to avoid that non-locality, we basically have to say there are these so-called hidden variables, like the particle had some definite spin all along, and quantum mechanics just doesn't know about that, and so the wave function description is incomplete. So that's EPR, or at least that's kind of like what Einstein had in mind. So do you want to interject any like follow-up questions about that, or should I explain how that relates to Bell's theorem?
Yeah, I think I'm pretty much in agreement with everything you said. So yeah, why don't you go on and talk a little bit about Bell, and then we can discuss.
So it's actually pretty simple. So Bell came along and read about Einstein's argument and was like, oh yeah, that makes sense. Obviously we need hidden variables to avoid non-locality, because non-locality would conflict with relativity and that would be crazy. And so he started wondering about the possibility of avoiding non-locality by having hidden variables. And I guess part of the historical background here too is that Bohm had come along in 1952 and created what's now sometimes called the pilot wave theory, which is kind of a hidden variables theory of the sort that Einstein maybe liked, but it was not a hidden variables theory of the sort that Einstein wanted in the context of EPR argument, because it was non-local, okay? And so Bell was sort of putting all these pieces together, and he was thinking, maybe there's some way to have a hidden variable theory, kind of like in the style of Bohm's pilot wave theory, but which avoids the non-locality, because he was basically like, well, what's the point of introducing this new theory if we don't get rid of the sort of most profoundly problematic thing about ordinary quantum mechanics, namely the non-locality that Einstein had pointed out was there. Okay, so I mean, sort of leaving aside the technical details, even though, as you pointed out, they're not really terribly complicated. People can find nice explanations of this online and in various books and things. But basically, Bell ended up proving that the kind of theory that Einstein showed you need to have in order to avoid non-locality, namely a theory in which every particle is sort of like got built into its detailed structure somehow, like how it will respond to some measurement of spin along a given axis or something. Every theory of that type that's local makes predictions for a certain slightly more sophisticated category of experiment that's different from quantum mechanics. The so-called local hidden variable theories make predictions for this type of experiment that are constrained by a so-called Bell inequality. And we probably don't need to go into more detail than that, but suffice it to say, okay, you go and do the experiment and it turns out Bell's inequalities are violated. So this class of theories, the local hidden variable theories, are ruled out by experiment. And that's kind of where all the fun starts, because usually then people say things like, aha, okay, so we get this contradiction with experiment by assuming locality and hidden variables. And then there's like sort of a handful of slightly more obscure things that people like to kind of claim are assumed in the derivation of the inequalities, like counterfactual definiteness. And sometimes people say sort of more obviously falsely that like determinism is an assumption. But in any case, you know, the idea is there's locality and then there's some other stuff that supposedly goes into, you know, Bell's theorem. And so we have to kind of like drop one of those assumptions now that we know that they, you know, jointly contradict experiment. And that is all basically just completely wrong-headed. It's just completely confused. It's completely wrong. And the reason it's completely wrong and confused is that the people who say that have simply forgotten about Einstein's argument, which, to recap, proves that the one and only way to avoid non-locality in the first place, in the context of this like much simpler sort of subset of possible experiments that you might do, where you're literally just like measuring the spin component of the two particles along the same direction on both sides. That is like having these sort of like deterministic hidden variable theories that obey counterfactual definiteness and whatever other things you want to add to the list. You have to have a theory with all those properties in order to avoid the non-locality. And so what Bell was doing was simply closing sort of the last open loophole for avoiding non-locality. And so the proper conclusion at the end of the day is that we have to have non-locality, period. Except it's not really a period, it should be a semicolon, because now you're going to ask me about like Everett and, you know,
well, I mean,
causation and lots of other things.
I know, well, I don't want to get too far into the weeds, but you know, I know there was a, you know, part of where this is coming from is there was a debate a few years ago, a debate raging in the literature about the significance of Bell's theorem, which you participated in, and quite forcefully made the argument that you've just made there. But I mean, there is, I mean, so yeah, so there was this argument about whether there exists two versions of Bell's theorem or not. And, you know, I'm not myself that interested in the debate about whether historically, whether historically John Bell thought he proved two different things. But I am interested in the question of whether there's more than one way of looking at the results. So, I mean, I think that, you know, so long as you're taking any kind of scientific realist point of view, that you know, that's what we started about, that, you know, the theory has to be about stuff, even if that stuff isn't localized in space-time, but the theory has to be about some stuff and how it behaves.
Yeah.
Then you know, and discounting many worlds and things like that. Then the explanation that you've given is one that I agree with. But there are people who take this sort of more Copenhagenish type of view, this slightly less realist point of view, and And they're typically the ones saying that, oh, there's another version of Bell's theorem which you could get around. You can get away with not having with having locality. You could have locality providing, providing things are indeterministic in some way. So this is like the catchphrase is Asher Perez's quote, "Unperformed measurements have no results." And so there, I think it's like, okay, so there's no, to somebody who takes that point of view, they're basically taking the point of view that non-locality means signaling, right? So if there's some possibility in the theory that you're talking about to send a superluminal signal, a signal faster than light, even if doing so would require knowing more about the state of the system than we actually do know, but if that's possible in principle to do in your theory, then that's non-locality, and anything else isn't non-locality. And then if you take that point of view on what non-locality is, then then what they say about Bell's theorem is, sort of strictly speaking, right. You could have a non-deterministic theory that satisfies that. It's just, it's a different, it's a different starting point for what what we take as read what a theory should be about. I don't know if you agree that that's.
Yeah, I mean, it feels a little bit like, to me, like you're kind of running together several related but slightly different sort of sub-controversies, like in this general vicinity. But maybe you're kind of doing that on purpose. I mean, I agree with you that sort of like going into the like sort of textual analysis of like exactly what Bell probably meant by some word or phrase in 1964 as against what he might have meant by that same word, a decade later or something. That's probably like way too in the weeds for this discussion. But at least sort of like one of the sort of sub-controversies that you were referring to, I think is actually about that, as opposed to being about, this other sort of more Copenhagen-ish idea. But let me say something about that, because I mean, I think that's the thing that's kind of like interesting. So it's certainly true that like there are a number of different, perfectly legitimate things, distinct things that one might mean by the word locality. And so, a lot of the controversy, such as it is about Bell's theorem, I do agree with you, comes down to sort of miscommunication or misunderstanding about what is meant by that word. So as you mentioned, one possible thing that someone might mean is something like the ability to, communicate, like send a signal faster than the speed of light. So that would for sure constitute a kind of non-locality, which would be, very difficult to reconcile with the theory of relativity. Like you could, text message your cousin to, text message your grandmother to never have a child, and sort of give rise to logical paradoxes if this were possible. So for sure, that's, something that one could mean. That, however, is not what Bell meant. And I think everybody involved in the sort of previously alluded to sub-controversy agrees at least that is not what Bell meant by locality as of, maybe the mid 70s to 80s or something. There's maybe some controversy about what he meant as of 1964. But in any case, what Bell sort of at least ultimately meant by locality was not at all this notion of like sending, a restriction on the speed with which one can communicate, but was rather something more fundamental, something about the speed with which causal influences, whether harnessable by humans or other sentient creatures to build some kind of telephone device or not, how fast those causal influences can propagate. And so even to make such a distinction requires one to be sort of comfortable in principle with the idea that there might exist causal influences in nature that are, for some reason, in principle, not harnessable by, humans to build a telephone. I'm comfortable with that, and I don't really understand why other people would not be comfortable with that. But I mean, the sort of argument for like, well, which of those, notions of locality should we care about? I mean, maybe I should clarify too, like, so Bell's theorem, the thing that I'm claiming at least sort of modulo worries about many worlds, or maybe backwards in time causation, or sort of like, you know, fairly strange ideas. Leaving such things aside, then what I want to claim Bell proved, or really sort of the more recent experiments sort of proved in light of Bell's theorem, is that non-locality, the existence of faster than light causal influences in nature, like that's a real thing that really exists. And it's very difficult to understand how to reconcile that with relativity theory. And so that's a sort of big project on the future that physicists need to like confront and try to deal with. But the claim is that that's what Bell proved. I mean, I think part of what you're saying is like, well, there are people who don't buy that. And one of the reasons they don't buy that is that they think that something distinct from that should be meant by the word locality, or they reject the idea that there could even be this sort of alternative meaning to the word locality that makes any kind of sense. It's somehow like too realistic, too divorced from kind of like what we can measure and build and communicate with and that kind of thing. It's sort of more realist and less operationalist. Anyway.
Yeah. Okay. Well, I mean, so I don't think we're going to resolve that controversy this evening.
Probably not.
Probably not. But we have a few minutes left. I mean, so I think we should talk about interpretations a little bit. To my mind, by the way, the interpretation of quantum, like talking about specific interpretations of quantum mechanics or getting into the details of them, is one of the least important topics in quantum foundations. And that's primarily because I think that they're all likely to be wrong. I mean, as you said earlier, I think it's extremely useful to understand things like the Broglie-Bohm theory, because it does give you a counterexample to so many claims. But so I'm not somebody who thinks we should resolve the interpretation question by sort of opinions or surveys. But nonetheless, having said that, maybe let's start. I'd be interested to know how you rank. So there's kind of the way I view it, and is that there's a big four interpretations, right? There are dozens and dozens of interpretations of quantum mechanics, but there are four kinds of interpretations that get talked about a lot. There are four that you talk about these four interpretations in your textbook. So I can tell you how I rank them, and you can tell me how you rank them, and we'll discuss why we disagree. So
and then we'll find out who's right in the election in 2 weeks, right?
Well, I would like, by the way, I would like it if in these conversations either somebody manages to convince me that I'm wrong about something, or I manage to convince somebody else that they're wrong about something. That would tell me that we're making some progress. But so I need to preface this by saying that my number one choice, as I've mentioned earlier, is none of them, right? So I really think there's a very big gap between that and the rest of my ranking.
But that's not one of the four. That's like number 5 that comes in first.
That's option 5. It comes in first. And then I kind of rank, see, this is very different from you, but I Copenhagen-ish style interpretations, by which I mean modern variants, not the work of Bohr and Heisenberg, and the many worlds interpretation together. I rank them about the same. And then it's the Broglie-Bohm theory. And then at the very last is spontaneous collapse. And I also have to say there's a very, very large gap between the Broglie-Bohm and spontaneous collapse. I really, really have a hard time understanding why anybody thinks that's a viable possibility. But I mean, maybe we can talk about these options in a bit more detail, but maybe you can tell me your ordering of them.
Yeah, sure. I mean, it would be interesting to kind of hear more about why there's these gaps that are the size they are and that kind of thing. But yeah, I definitely would have a different ranking. So for sure, the pilot wave theory would be at the top. Although, I mean, now that you've said there's the big four, but then there's also this wild card, none of the above option, maybe I should think about exactly where I would place that. Maybe I'll postpone to the end of my list where that fits, because it's going to kind of be off to the side in an orthogonal direction or something, I suspect. But of the four, I think the pilot wave theory is by far the best in lots of different ways. I would probably put spontaneous collapse theory and many worlds kind of fairly close together as a fairly distant second. And if you force me to kind of like break that tie, I would probably give the nod to spontaneous collapse theory, even though I have to say, I find it to be a kind of hot mess, which basically cannot be taken seriously as a fundamental physical theory, but it nevertheless has an important leg up on the Everett theory, because it at least permits a coherent story about local beables. So, or at least that's a kind of relatively popular thing for adherents of spontaneous collapse theories to recognize the need for, whereas fans of Everett seem to resist even admitting that there's any such problem as that they need to say even some like sort of vague hand wavy words about. So, but you see, that's a kind of like subjective ranking that's almost more about the people advocating for the theories than it is about the theories themselves. And then there's like this sort of like enormous, vast, empty space. And then well down below those other three is the Copenhagen interpretation, or any modern variant thereof. Although I suspect that if we take some more time to talk about this and you elaborate on what exactly do you kind of mean by the Copenhagen and modern variants of the Copenhagen interpretation, my suspicion would be that you would kind of end up saying roughly like, well, they're kind of like fancy ways of saying none of the above, and they're sort of like placeholders that might eventually push us in the direction of an actual coherent physical theory, but none of them are that.
Well, I'm not sure that's what I mean, but I mean, I think the thing that we probably agree about spontaneous collapse theories more than disagree about them. I mean, my reason for disliking them is this, because I think that, you know, there's a lot of physicists who think this way. You know, we were talking earlier about the measurement problem, you know, and there's a lot of people who have the idea that, oh, if only we could get the wave function to collapse.
Right.
If only we could get the wave function to collapse, would be done. So this is kind of, to my mind, the thinking that's behind starting to develop a spontaneous collapse theory.
Absolutely, yeah.
So then you do that, you get a theory where the wave function collapses, and then you look at it and you say, huh, I still don't know what that thing says. So as you said, then you know, a lot of the adherents of these theories go ahead and they then add local beables to it, like a mass density or particle flashes or this and that and the other. Right. And at the end of that, they've ended up with something that's far more similar to the Broglie-Bohm theory than it was ever supposed to be initially, in the sense that, you know, it's a theory about the evolution of these local beables. That's and right. Furthermore, it disagrees with quantum mechanics in certain experiments that we haven't done yet. And, you know, I think it's highly plausible that they'll get ruled out in my lifetime. So, you know, at the expense of introducing a theory which is very, very much like the Broglie-Bohm theory, which already is capable of reproducing the predictions of quantum mechanics,
right?
You end up with a theory that I think is likely to be ruled out. So that's, to my view, to my mind, why it's so far down.
Yeah, I mean, it's kind of curious, because I completely agree with literally every word you just said about that. It's sort of like the whole guts of the idea are this sort of Frankenstein monstrosity that's like an attempt to take something, namely sort of the textbook rules of quantum mechanics, right? So, you know, I mean, we've sort of referred to the measurement problem. Maybe it's worth kind of saying cleanly what that is. Like, quantum mechanics says, look, you describe quantum systems in terms of this wave function thing, and here's how it evolves in time. There's like a partial differential equation that says how this object evolves in time. But then there's this sort of like asterisk, and you look down and it turns out, oh, there's a footnote that says like, yeah, but actually that's what happens only kind of most of the time. And then every once in a while, when you make a measurement, this other like, mathematically distinct time evolution occurs, the so-called collapse of the wave function. And it's like, that just can't be right. I mean, any sort of like half, conscious person who looks at that can see in a second that it just, like some story like that says, look, most of the time, here's what happens, but then every once in a while, and by the way, what I mean by every once in a while involves this word, namely measurement, that like is some kind of high level human activity. Like that word just simply does not belong in the fundamental laws of nature. So every once in a while when a measurement happens, this other thing happens, like that just can't be the right sort of fundamental dynamics for the theory. So that's the measurement problem. And I mean, I think what you were describing, and I completely agree, is that the spontaneous collapse theories sort of seem like a way of taking this I don't know, like contradictory set of dynamical evolution rules and just like cramming them together into kind of like one sort of Frankenstein monster thing in sort of the crudest imaginable way. So that's at least what I meant when I said like I kind of can't take this very seriously as a physical theory. So and I get the impression that that's more or less your attitude as well. But then I guess, I mean, I don't know, like even despite that, like for me, to kind of come back to the point we started with, like, look, the goal at the end of the day is to figure out how to account for, tables and chairs and the needles on measurement pointers and the sort of statistics of how often they go this way as opposed to this way. Like literally everything that there is to explain is something about how some physical stuff in three-dimensional space is like moving around. And at the end of the day, these spontaneous collapse theories with the sort of, extra bonus local beables of one flavor or another added on, those actually succeed at doing this. And I think that is a kind of important achievement that should not be discounted, even if, I don't know, sort of like in our kind of theorist bones, we know it can't be right at the end of the day. It's still like an achievement that I wish, Everett would aspire to at least trying to match. So I think we need to respect it for at least that reason, even if we agree that it's probably not right, and probably, I agree, will be known to be not right within, I don't know, another decade or two.
Okay. I don't think we should take up too much time, but let's just continue this for a little bit.
Okay.
Yeah, part of the reason why I put many worlds in Copenhagen so high is, it's two reasons. So one is a minor reason, really. You may think it's a major reason, but there's at least a claim in those theories that they're able to evade non-locality. And so you might have thought that if we want to have fundamental relativity, they would be better choices. But that's not really the main reason. It's sort of more how I view the explanatory structure. It's like, sort of going after Einstein, the way Einstein formulated special relativity. It's like you have these physical postulates, very clear physical postulates of special relativity, that at first sight seem to be completely contradictory. But then you realize that if you get rid of an assumption that you are holding dear to, like what is the structure of space and time, basically, that you make them fit together. Yeah. And they kind of have to my mind, I think the correct interpretation of quantum mechanics, not that we have it yet, is going to have something like that surprising flavor to it. And there is sort of an element of that in these two. It's like, taking the assumption, for instance, that it's just the universal wave function evolving unitarily, and that's the whole thing, like just the evolution of the wave function, no collapse. Yeah. And, I don't want to go into the weeds with the details of many worlds in Copenhagen, but, I think you can more or less derive what they're supposed to say about reality from something like 4 principles each. And those 4 principles are principles that at first sight seem contradictory, but none of those principles are, in the case of Everett, none of those principles are, I postulate that there are many worlds. they are much more reasonable sounding things than that. And then you derive that, you know, something that you presupposed, that there was only a single world, has to go. And so I kind of like that structure of an explanation. I don't think either of those explanations are actually right, but I like the fact that what they're trying to do is something, you know, trying to maintain some kind of reasonable sounding postulates or principles, and then you know, as a result of that, having to discard something which, you know, which is like an assumption that we would normally make, a common sense assumption that we would normally make. So I think that even though I don't think that either of those interpretations are correct, I think that something of that structure of explanation is going to ultimately be the right sort of idea.
Yeah, I mean, I agree with you, especially about Everett. I mean, I completely agree with what you said. The Everett theory is like kind of beautiful and elegant in its simplicity. And I completely agree with what you said about how like it seems like it's saying something that sounds crazy when you first hear it, but then the theory itself, at least sort of, you know, purportedly explains why the part that sounds crazy actually is completely compatible with what we take our ordinary experience to be. And so you're sort of left with a nice, clean account of how it's not actually crazy at the end. So, I mean, I think we're on the same page about that, but then I'd be very interested to hear, I don't know, like, how do you think about the ontology problem for Everett? So like, I remember, you know, I watched your show with Sean Carroll a couple weeks ago, and you, I think, tried to push him on this sort of just a little bit, which I appreciated very much, because not enough people try to do that with, you know, talking to these Everettian people. But he didn't really, I think, give any answer that I was able to understand. Do you have a sense of how you would answer that sort of on behalf of an Everettian, even if you're not one yourself?
I mean, I think there's a partially incomplete story. I mean, part of the trouble with whenever you're talking about emergent notions is that they're always going to be fuzzy. Emergence is a fuzzy concept, you know, just as in thermodynamics, for instance, we never get the rules of thermodynamics exactly. We only get them, you know, to a very good statistical approximation. So there's only ever going to be, so if you buy the Everett account, there's only ever going to be some sort of fuzzy classical reality. And there's a question of whether, you know, can we make sense of...
Hang on, so what's fuzzy? I mean, if literally you meant, well, it turns out really don't have infinitely sharp edges, but there's like a little blur, like, I mean, nobody has a problem with that. So what you mean by fuzzy is very different than like the picture of reality in, you know, of matter in three-dimensional space provided by the theory is a fuzzy picture. Because I mean, I certainly would have no objection to that. I don't think anybody would.
I mean, I think that there's going to be...
The story of emergence is somehow fuzzy, but that's a more serious problem, right?
Yeah, I mean, okay. I mean, the thing is this, I mean, I don't really want to speak for the Everettians, because there's
but somebody has to try.
There are going to be multiple different versions of it that approved by different subcamps of the Everettians, right? So, you know, the story is supposed to have something to do with the idea of decoherence and the idea that you can identify stable structures that roughly look like our own three-dimensional universe, and you're roughly going to
look like in what sense?
Well, I mean, you know, if you look into
they don't literally look like it.
If you look into the theory of decoherence, you're going to have something like it within the branches, at least on a coarse-grained level, you're going to have within the branches, you know, macroscopic objects described by wave functions which are relatively well localized in position and momentum. You know, I don't want to get into the technical terms, but, you know, coherent states and things like that evolve roughly according to the classical equations of motion, and that's only going to be true at a certain level of coarse graining. And you can see that there's a skeleton of that kind of story available from the theory of decoherence. Have all of the details of it been precisely pinned down? I'm not sure. I don't feel confident to say that, but
I think my concern, I don't think, is primarily about those details. I mean, yes, like decoherence is a real thing and it's important, and it clearly would need to play some important role in this story. But I mean, I just kind of want you or us or someone to just like slow down. So like literally you said things like, look, the wave function has these branches. So first of all, the wave function is, a complex valued field in some ridiculously high dimensional space. Yeah. It has branches. Okay, that just means that it's not sort of homogeneously spread out over huge regions of that space, but there's like little localized islands of it where it has support with kind of empty space in between. So a branch is like some localized island, in this configuration space of the wave function. And you spoke about coarse graining. So, I mean, literally just in the naive, straightforward sense, if you coarse grain this like lump of, wave function in the 3n dimensional space, you get, well, I don't know, something in 3n dimensional space. It's like a coarse grained lump, or, a slightly less detailed description of a lump of stuff in 3-dimensional space, 3n dimensional space. The question is like, how do we suddenly have real physical things in 3-dimensional space? Like, where does that come from? Because I don't think that comes from decoherence, and I don't think anybody would say that comes from decoherence, but I don't know where it's supposed to come from. I just don't get it at all.
Okay, well, I mean, we should probably conclude in a minute, but I mean, I think the idea is that, okay, so most states in this abstract 3-dimensional space don't correspond, 3n dimensional space don't correspond to anything in 3 space as well, but certain states do. Certain states look like uncorrelated, but a bunch of n uncorrelated particles, each having a position in space, right?
But they don't look like that. You can say they correspond to that, and I know mathematically what you mean. You mean, oh, like a well-localized lump in configuration space. That's, that coarse grains to a point in configuration space, which mathematically can indeed correspond to the configuration of n particles in 3 space. But are you saying we have n particles in 3 space? Like, where did those come from? Because a minute ago they didn't exist, and the fact that there's some mathematical correspondence makes them magically pop into existence all of a sudden.
The claim is, I think, that if you have such a state, then it would look like, to you, the observer, it would look like you had n particles in 3-dimensional space, and that's, there are always sort of claims about, there's always implicit, in many worlds and things like that, certain claims about the nature of realism and the nature of how conscious experience works, which are, not supposed to be part of the of the ontology, but you sort of have to make a sort of certain assumptions about them in order for the theory to work at all. Yeah. And I think that there's a much longer discussion to be had about whether that there's this idea of structural realism, such that that if you have something that has, well, it's not really structural realism, but it's just if you can identify some structure that has the same properties as Y, then it is Y, right? And this is a kind of claim that you could dispute, of course, but it is part of what they're saying.
Yeah, I mean, I literally will just say 2 sentences and then we can move on to whatever we need to move on to. But part of the way you put that at the very end, I thought was actually clarifying that the idea is supposed to be that well, if you're an observer who's, part of this lump of wave function in the high dimensional space, then to you, it looks like there's, tables and chairs or something. I mean, I think it would be it would move the discussion forward, in my opinion, if we could at least get a kind of clear statement of whether that's actually the story. Because to me, there's a big difference between saying the theory accounts for the real existence of 3-dimensional objects in ordinary physical space, which I think is what we want and need. There's a difference between that and saying the theory accounts for the appearance of such things, the, one might say, delusional appearance of such things. Those are two very different stories, and one of them is sort of embarrassingly bound up in like consciousness and how things look, and it starts to feel really uncomfortable to me as a theory of physics.
Yeah, well, I mean, I certainly think that, you know, if ever it is true, we must be radically incorrect about our, you know, about our everyday assumptions about what exists, right? It's like, you know, even if you buy their approach to the emergence of the three-dimensional world, it's not just our three-dimensional world that's emerging, it's many of them, which is a very different thing. So
yeah,
I mean,
to me, many of them, like the idea that there might be many of them or many sort of like parallel non-interacting things overlapping in space, like, okay, I'm open to that. To me, that's much easier to sort of accept as a sensible possibility than this sort of magic about getting some stuff in three-dimensional space in the first place, which I just find completely incoherent. So if Everettians could convince me that they can do that, and then the only sort of difficult thing is like, yeah, but there's like too much stuff in, you know, three-dimensional space, and there's like all these parallel non-interacting copies of everything, like, cool, I'm totally willing to swallow that. That's relatively unproblematic for me. So
okay, well, I mean, I think we're not going to solve the problem of interpretation of quantum mechanics in one evening. And so I think we should probably, unfortunately, I think we should probably conclude the main part of the discussion here, because I want to have some time for a Q&A. Before we do that, though, I just want to mention our next event to anybody who's watching. We are going to be having a bit of a break from the quantum discussions next month. We're going to be talking about space science. Actually, we are going to have Kate Green, who was part of the NASA High Seas mission in Hawaii, where she lived on a simulated Martian environment for something like 3 months. So we're going to have a discussion with her. It'll be on November the 11th, same time, same channel. And that will be a discussion between her and two Chapman faculty, Anna Leahy and Doug Deschaux. And they are also authors of a book about space. It's called Generation Space. So we're going to have a break from the quantum and a nice space science discussion. But I am planning to keep talking to many more interesting people who work on quantum mechanics. And so this series will definitely be continuing as well. So look out for announcements about that. So thanks, Travis, for joining us. I'm going to open it up to the audience. Kai, you can bring some questions from the chat room into here, please.
Yeah, we have a few questions already lined up. So the first one is for Travis. Where do you think quantum mechanics, quantum theory will fail? Or do you think it won't fail? Akin to Newton's gravity failing with the orbit of Mercury?
I have no idea. I wouldn't, feign hypotheses. I would be highly surprised if it fails in the ways that are predicted by spontaneous collapse theories, just to connect back to that earlier part of our discussion, just because I sort of don't get the feeling that those particular theories are likely to be true. And I'm quite impressed by the empirical success of standard textbook quantum mechanics. So I wouldn't be surprised if it never failed. I don't know. So who knows? But I hope it does, because that would certainly be more interesting and would probably be the kind of jolt of empirical reality that might somehow help us get out of this like slightly stagnant situation that we're in, like arguing about the currently extant interpretations of quantum mechanics. So
yeah, I mean, from my perspective, I don't think quantum mechanics is going to break down in order to help solve the measurement problem, like in a spontaneous collapse theory. But I don't think that it's a macroscopic number of particles limit. I do, however, think that there's every reason to think that, all our theories of physics will break down as if we go to sufficiently high energies. It's always been higher and higher energies that have been pushing the limits of what we can see. The difficulty is there's limits to what we can do in practical experiments that we can do here on Earth. But even though quantum field theory is enormously successful, if quantum theory is going to break down anywhere, it's going to be at sufficiently high energies, much higher than we've been able to access in current particle accelerators. So,
but Matt, when you say quantum field theory, it's maybe unclear whether you mean sort of like the generalized framework of quantum field theory, or whether you mean like the current version of the standard model.
I don't mean the standard model. I mean the whole structure of the theory. And if it's replaced by anything, there are various problems that theorists are having, placing, trying to unify the forces and things like this, the hierarchy problem, the various problems that high energy physicists are trying to solve, that are being solved currently in very controversial ways. I think it should be at least on the table that one of the ways of getting around this problem might be that quantum theory itself gets replaced by a new framework. And that framework, by the way, may not make any of these problems that we're talking about better. It might actually make them worse. It might be replaced by an even weirder and more strange theory. And if I had to bet, I would suggest that would be more likely than something that would actually help us solve these problems we're talking about now.
And is that just based on general pessimism about how the world is working out so far this year, or?
Partly, but also, I think that something like the measurement problem is the kind of thing that's going to go away when we have the right framework of understanding.
Mm-hmm.
So if it gets replaced by nature isn't going to be governed by a different theory just because of anthropocentric concerns, right? So, as we go to further and further away from the realm of our everyday experience, it kind of like makes sense that the theory of physics will get less and less easy to understand in some sense. I don't know. I mean, it's just speculation. I have no idea how to go about doing any of these things. So, yeah. Okay, Kai, do we have another?
We have several, yeah. So the next question, do you think that relativistic quantum theories change our perspective on quantum foundations? In particular, the issue of having wave functions where there is no fixed number of particles?
I don't, for me personally, the answer is pretty much no. I mean, I tend to think that all of the foundational problems that can be identified in non-relativistic, quantum mechanics persist in these kind of more sophisticated theories like quantum field theory. It's sort of like easier to hide them there among the various mathematical sophistications. And so people kind of fool themselves into thinking like, oh, well, there's no measurement problem, or there's no ontology problem, or there's no locality problem, with quantum field theory or something, but there just is. So this might be slightly idiosyncratic, but I basically think no, none of those things have really changed my opinion about anything in the foundations. Although, of course, I remain sort of hopefully optimistic, maybe that like there'll be some new revolution and quantum field theory will break in the way that Matt was describing, and then we'll sort of have to be forced to come up with some new thing. And he was expressing sort of pessimism about that making any more sense than the quantum mechanics we currently have. But I don't know, for me at least, maybe there's room for hope that if we're forced to kind of start again from the ground up, maybe we're, as I'm about to say this, it starts to sound almost implausible given certain political realities of the time, but still maybe we're in like a better place culturally, at least sort of within physics. I mean, I really think we sort of got into this horrible situation in quantum foundations because somehow sort of like the philosophical culture of the physics community was just absolutely rotten kind of back in the early part of the 20th century. And it's unclear to me how much better it is, but it's clearly at least somewhat better. And I think there's a little more kind of like I don't know, unwillingness to put up with sort of obvious nonsense today. And so I would hope that sort of whenever that kind of rebuilding effort happens, which maybe could be spurred by the failure of relativistic quantum field theory or something, maybe we would build something that actually ends up better. So that's my hope.
All right, so the next one is, I guess, more of a challenge than a question. So when you say that psi-only ontologies fail because they don't explain the emergence of local beables, isn't sort of the challenge on you to define a constraint on what you mean by emergence?
Let me see if I understand the question. So I'm claiming that I don't understand how local beables emerge from the wave function, but somehow that's my problem for not defining emergence clearly enough. Am I understanding this right?
That's about as well as I understand the question, honestly. Maybe the person who asked it will post a follow-up.
Yeah, I mean, I would certainly welcome clarification. I don't know what to say. I mean, like I'm just the one putting up my arms, sort of saying, I don't understand how you get from here to here. And, you know, I've been wishing for 10 or 20 years that someone would simply explain it to me, because there are a lot of people who sort of act as if they understand it perfectly clearly. And I'm very much open to the possibility that there's some way of understanding this emergence, or maybe it's not really emergence, but is sort of the emergence of the mere appearance of a certain thing. See, I'm not even sort of quite clear on where the claim is that, you know, we can get, but I just don't see how we get there. So, you know, I'm all ears. But I guess I don't quite sort of get the idea that it's my fault for misunderstanding the concept of emergence or something. Like, please explain it to me if somebody thinks that I've misunderstood it.
All right, so I'll read the follow-on. Again, I'm not entirely sure that I follow, but I'll just read it as it's written. So
Cool.
Particles inside my cell are entangled. So to describe them, I need the higher dimensional wave function, but my cells are not entangled. So even the quantum description of them is 3D. Isn't that all there is to the emergence of 3D objects from a high dimensional wave function?
I mean, I don't know. The very first part of that was like, particles in my body are entangled. What particles? I mean, according to Everett, there's literally there are no such particles. There's this wave in a very unfamiliar, abstract, high-dimensional space. So like it sort of seems like maybe the questioner is taking for granted that there are clearly local beables, like the particles and cells that his or her body is made of, and thinking that there must be some clear and straightforward sense in which the quantum mechanical wave function is like providing a description of those things. But you see, that's like precisely the point that's at issue here. It doesn't. Or at least I don't know how it does, but you can't just sort of claim that those things are there and claim that there's also the wave function and sort of shrug as if to suggest that there's therefore obviously no problem. The problem is that I don't know how to find anything like particles or cells in three-dimensional space that might be arranged in the shape of a human body or whatever. I don't know how to find anything like that in the wave function of the universe.
All right, so this is the last question we have. So the special theory of relativity is a classical theory. Do you think it needs any form of reinterpretation or modification before it can be extended into the quantum realm? I guess this question relates to quantum field theory.
Does relativity need extension before it can be extended into the quantum realm? I guess I don't quite understand what it would even mean to extend it into the quantum realm. I mean, it seems like special relativity sort of tells a story about the space-time background on which sort of various material processes, as described perhaps by quantum mechanics, are playing out, and sort of the way to reconcile those things is sort of, you know, leaving aside issues like the measurement problem and the ontology problem, kind of like already with us with, you know, things like relativistic quantum field theory. So I guess, again, I'm not quite understanding what the question is getting at.
I mean, I can ask a related question, which is, of course, we don't yet have the theory of quantum gravity. And if you had to make a bet, the theory of quantum gravity just has to be some theory which unifies the two subjects, and in the appropriate limit, it's going to give you general relativity, and the appropriate limit, it's going to give you quantum field theory. If you had to guess which is more likely to break down, like the principles of which theory are likely to be better guides for constructing that theory. So you know, I feel like I'm in an increasingly small minority in physics, because I say it's basically the principles of general relativity that are more reliable. It's not going to be exactly the same theory, but something like some generalized version of those principles are going to underlie the actual theory. Whereas whether it looks anything like quantum mechanics or quantum theory is like completely up for grabs as far as I'm concerned. Most workers in this field seem to think it's going to be some sort of a quantum field theory, and you know, gravity is going to be completely emergent. I don't know. What's your take on that question?
Yeah, I think even more than you, I would just say I have no idea. I don't know how to try to predict how these things will play out. It's completely unclear. So I wouldn't even know how to bet.
Yeah, I'm just trying to ask if you're with Einstein or Bohr here, because you know, I want to preserve the principles of Einstein's most beautiful theory as much as we can. I mean, it's a beautiful explanatory structure to my mind.
Yeah, I mean, I certainly agree with that. And I don't know, I guess, as I said a minute ago, like, I think that quantum field theory is sort of not yet even really standard relativistic quantum field theory, like as explained and presented in standard textbooks, is like a sick theory. It suffers from the measurement problem, for example. So like, to me, it's sort of like, even your question is somehow like presuming a little too much. Like, look, we have this one thing that's unproblematic sort of within its domain of applicability, and we have this other thing that seems unproblematic within its domain, and then they don't play together nicely, and so it sort of at some point in some extended domain something's got to give. I just don't see it that way. And so maybe for that reason I'm kind of with you against the majority of most regular physicists, who I think would deny that there's any kind of like conceptual or foundational problem with quantum field theory. So with, like you, I think I have a higher sort of present level of respect for the integrity of general relativity than I do for sort of textbook quantum field theory. But I don't know, like, what that means, one true quantum theory of gravity is going to look like at the end of the day. Like, I don't have any idea, unfortunately. I wish I did.
Was there another question, Kai?
Yeah, we're running over time, but there's one more.
One more question then.
Yeah. So we have some work on modeling observers and causal systems, e.g. Kevin Knuth's work has derived quantum mechanics plus special relativity. Maybe physical order is emergent from epistemic constraints on observers and ontology as unreachable. And the actual question is, do you take approaches like this that are sort of observer-centric seriously?
I think that must be a question for you, Matt. That sounds like more like one of your Copenhagen-inspired contemporary views or something.
Do I take? I mean, well, I guess first you can answer that question. Do you take observer-centric approaches seriously? And I guess I know the answer to that, right?
Not really.
Yeah. So I'm open to all things, but there's a lot of, I mean, how should I mean, I don't know how to say this. I mean, there's lots of different approaches with lots of different starting points. I mean, I do think that ultimately, any approach to quantum mechanics that's going to work should say something about reality at some point along the way. There should be some statement about things that actually exist. I mean, I'm okay with adopting operational or information theoretic or observer-centric methodologies in order to derive things along the way, just as, you think about the relationship between thermodynamics and statistical mechanics, right? Thermodynamics is initially, in some sense, a completely operational theory. It's about things that you can do, processes that you can achieve, and it's just a set of laws which governs that. And if you just said, okay, we're not allowed to work on that kind of approach at all, you would never have managed to get thermodynamics into the right shape where you could give it a statistical mechanical explanation, right? Thermodynamics did not initially have the concept of entropy. Imagine trying to derive the second law of thermodynamics in the form that says, there is no heat engine which has, only the effect of, turning heat into work with no heat expenditure, right? That kind of version of the second law of thermodynamics. Imagine trying to derive that directly from statistical mechanics, as opposed to the statement entropy doesn't decrease. It's much easier to do the second. So it is worthwhile. And I'm very open to the possibility that the way we understand quantum mechanics, the equations that we write down, the way we write down the formalism right now, may not be the most conducive way to finding the correct solution, right? And I said this in the debate with in the discussion with Sean. Imagine somebody gave you classical mechanics in its most sophisticated form, say Lagrangian mechanics or something like that, without telling you anything about the ontology, and you had to try and figure that out. I think you'd have a hard time. So, I think there's definitely value in these approaches that take different starting. Don't try to say, okay, these are the things that exist in reality, this is how they behave, but try and sort of derive things from other types of principles, be they operational principles or epistemic principles or information theoretic principles. There's value to those kinds of approaches. I haven't seen anything to date where I look at it and I say, oh yeah, that's it, that's definitely the way of understanding things that's going to lead us to the correct approach. So, Kevin Knuth's stuff I don't like or dislike above and beyond anything else, that's try and take this kind of approach. I'm glad there are people trying to pursue these kind of approaches, but I haven't seen anything in it personally myself that sort of indicates this is the one true best way of doing things. That was a bit of a long-winded answer, but hope that's okay. Well, I've managed to give myself the last word instead of Travis. Thank you very much, Travis, for joining us this evening and for sticking around so long and answering people's questions. I enjoyed the conversation, and I hope everybody will join us next time we do this. But for now,